Hi, I'm Ed Sperling. I'm the Editorial Director of Low Power Engineering. I'm here with Aveek Sarkar, Vice President of Product Engineering and Support at ANSYS Apache. Aveek, we all know that power has been a major issue and a major thorn in a lot of designs, but what can we expect at the next process nodes?
So if we look at the industry and some of the recent commentaries from some of the leaders in the industry, let me quote, for example, from Dadi Palmuter's keynote at ISCC earlier in February. He talked about power as one of the key design constraints. And he mentioned three things that they are looking at to optimize power in some of their designs. One thing he touched upon is probably what's near threshold computing or loading the threshold voltage. What he alluded to was to reduce the supply voltage of the chip to threshold voltage levels. Now, if you reduce the supply voltage close to the threshold voltage, the noise margin degrades considerably and it reduces. The second thing he touched upon was to reduce power through the use of 3D ICs. And there, the primary goal is to reduce the power of the I/O circuit. The third area he touched upon was to use on-chip regulators to minimize the impact of package and board PDN or power delivery network traces. So all three areas are what we focus on in terms of power delivery integrity. Also, if you look at a comment from Mike Muller, he's the CTO of ARM. He also touched upon near threshold computing as one way to reduce the power consumption because power is obviously related quadratically to supply voltage. Now, if we work on sub-threshold voltage levels or supply voltages at such low levels, we have to model the power noise very carefully. So that's one of the critical challenges that designers have to face is how do you predict the supply noise on the chip in the presence of the package and the board traces for different operating modes of the chip. And once you have predicted that supply voltage, how do you assess its impact on the chip's performance and its reliability?
Are definitely getting harder with third-party IP being now thrown into the mix. How do we deal with that? What do we have to do to enable integration?
There are certain leap of faith, if you will, that you have to take when you bring in a third-party IP. You may not completely understand what was done to validate that IP from different aspects. The two areas that I'll focus on is from power itself and reliability. So let's say you're taking an IP and you're going to put it in a 20 nanometer technology or something lower. Then you have to worry about has it been designed to meet the foundry's requirements for power electromigration, for signal line electromigration, or from an ESD point of view. And once you have verified the IP by itself, it does not stop right there. You have to make sure that the IP is integrated properly at the SoC level, it is connected, and it's properly functioning inside the full system context.
We've got a lot of things that we have to model. How do we go about modeling complex designs? What needs to be done?
So let me use the whiteboard to explain what we are looking at inside Apache to do. IP comes in various forms. Obviously, you have soft IP, and you're working at the RTL stage. And then you go into the physical design, or when you're implementing the SoC. In parallel, you also have, say, the analog IP, the memories. So let me separate these out into two categories, RTL and analog IP. And when you're doing the physical design, you're integrating and bringing all of these together, hardening them, and creating the final chip, and then putting it inside the package. Now, when we think of IP inside Apache, we are looking at ensuring that the data sharing for all these different teams happen in a seamless manner. So when you have an RTL designer who is working on optimizing their particular netlist from a power consumption point of view, they will use Power Artist to look at different parts of the design, to estimate the power at an RTL stage, and also to find reduction opportunities to meet their power budget. They will explore their design through the graphical user interface or through automatic reduction techniques. And once they have done that, they will create a model, and we call that RTL power model, that will go into the physical design space and will help increase the coverage of the sign-off process. When we analyze an analog IP, our customers use a technology called Totem. It's qualified down to 20 nanometer technologies for extraction, for ESD, for electromigration, And once they have validated the IP, they create a compact macro model. It's an encrypted version of the design that is suitable for system level, SoC level validation. Obviously, from the package, we have to bring in a model, and that can be in an S parameter format. And all of this is integrated inside a full chip simulation framework like Red Hawk, and can use to validate the RTL, the analog IPs, the package, all in one environment. And at the end of the process, we write out a chip power model that can then go into the system level for the package, chip, and the PCB sign-off.
What breaks at 20 nanometers, and what do we have to do at the future process nodes?
20 nanometer obviously introduces a lot of complex processing changes. We have seen technologies like dual pattern etching. There have been talks about using local interconnects below the metal layer, metal one layer, to connect the different contacts that are present in the technology. Obviously, there are a lot of process-related changes that are happening. In terms of design also, we are seeing people taking advantage of the higher levels of integration, the smaller size, the lower leakage power, to put more devices together in the same SoC. We are seeing a shift to the use of more processor cores in the same piece of silicon, along with different type of analog IP, SerDes, PHY, GPS, all the different type of radios are now sitting on the same piece of silicon. So 20 nanometer is obviously, there are a lot of process related challenges that we have to deal with related to electromigration. That's going to be one of the biggest challenges that designers have to face. ESD, making sure that the device can actually operate and meet the ESD sign-off standards is going to become very critical. And obviously integrating all these different type of IPs and make sure all of them function in an SoC and a system level concept is becoming very important.
We're hearing a lot more about 20 nanometers now than we ever had in the past. We're starting to see a lot of interest in that process node. What has to change at 20 nanometers?
20 nanometer, as I mentioned earlier, definitely brings a lot of process-related complexities and also a lot of design challenges. So let me take a step back and look at some of what were we doing for prior to 20 nanometer. So we were looking at an SoC. We were solving dynamic voltage drop, what we call DVD. We were looking at static power electromigration. We were also looking at ways an IP can be validated standalone and it could be brought into the SoC. We were also working on enabling what we call chip package system co-design. And that within the construct of Apache being as part of ANSYS and working with a lot of the electromagnetic simulation technologies that ANSYS has, like HFSS, SI wave, we are creating an ecosystem for that. The new areas for 20 nanometer that we are looking at, the first is what we call RTL to gate methodology. The second for 3D IC enablement. And obviously, we have to get ready for the EM rules and the ESD simulation criteria for 20 nanometers. So let me first focus on the RTL to gate, because this is a very new concept that we are seeing many of our customers adopt based on the technologies that we are providing. The whole premise of RTL to gate methodology is to leverage RTL level simulations to get early visibility into the physical design and to get better sign-off coverage. At the RTL level, we have better access to vectors because we are running functional verifications, we are running power traces. Now, at the RTL level, because we have those vectors, we have a lot of cycles of simulations. Using PowerArtist, we can identify very quickly which are the power critical frames in that vector or in these sets of vectors. And we can capture the relevant information through this RTL power model. And then we pass that to Red Hawk. And what Red Hawk will do is to perform early power grid prototyping. It will enable more accurate sign-off process by leveraging the RTL VCD information. And that's what we call the RTL to gate power methodology. Obviously, inside Red Hawk, we had to enable new engines to support this capability. In our next generation of Red Hawk, which we recently released, we have a new logic engine, we have a new state propagation engine, which are very new and probably the first time in the industry.
This gets even more complex as we start stacking die, because what you have here may function well at 20 nanometers, but your 20 nanometer chip may be connected to something that's sitting at 65 or 90 or 130. How do you deal with that?
3D ICs obviously is a very interesting challenge. The goals of 3D IC are often taken as reducing the overall, maybe the form, the size of the design, or to enable, as you said, heterogeneous integration to mix and match different technologies. But one overlooked aspect of it, it helps reduce the power consumption because it brings the chips closer together. So the overall I/O circuit power can actually come down considerably. So there are multiple benefits that 3D IC or stacked die 2.5D designs can bring to us. But what are some of the challenges that we see customers face? So let's say this is an interposer. And let's say you have a logic die and you have a memory die sitting next to each other. And obviously you have the package here. The key challenge now for the logic designer is instead of getting the power directly from the package, their design now gets powered through the interposer. So there is an additional stack of metals coming in the path. Now some of these domains can also be shared with the memory. So you have the noise coupling between the logic and the memory dies. So we have to simulate for power integrity for the whole system together. The logic, the memory, the interposer, and the package simultaneously. Other key challenges, you may not have access to the layout of the memory die. You are designing the logic and the interposer. So then you need to get good models that can mimic the electrical behavior of the memory die and allow you the full picture. So we are working with SI2 to enable the standardization of such a model. Power obviously is one key area. The second is what we focus on is thermal analysis. These chips, they are obviously generating heat, but there is less room for the heat to go out from. And there are more heat sources. And the heat generated by the logic chip will impact the memory chip. Our power and thermal analysis flow is now part of the TSMC's reference flow to enable this entire system to be simulated simultaneously together.
Aveek, Sarkar, thank you very much for your time.